In this video, I'm going to walk through my process of better understanding the contents of ivf.pid.pt, which is one of the main index artifacts created when you create a ColBERT index. I'm going to start with a very short presentation to set up some background information, and then I'm going to walk through code. So the ivf.pid.pt file contains two tensors. First is ivf, which is the sequence of unique passage IDs for each centroid concatenated together. And then we have ivf lengths, which is also a tensor where each value is the number of unique passage IDs for the centroid IDs that it corresponds to, where the centroid IDs are the indices of that tensor. So before we get to that, I want to set the stage on how we actually get to some of the main components that are created, specifically this codes object that we'll see. And this is what it looks like, generally speaking, when you are indexing with ColBERT. So I have some config with a ColBERT config object. I instantiate an indexer given this checkpoint and the config, and then I call indexer.index, and that's what actually does the indexing, and it creates an index with this value, dataset name underscore ColBERT underscore index, and it's indexing, in this case, these 1,000 passages. In this case, I'm indexing the conditional QA dataset that's part of the UKP Lab DAPR collection. So what is that indexer.index? So let's look at the indexer, and here's the index method, and inside the main thing I'm going to focus on is that it calls underscore underscore launch, and it passes to launch the collection. So in this case, it's our list of passages. So if we look at underscore underscore launch, there's a couple different ways, but reading this comment here, it encodes collection into index using the collection indexer class. So that's what launcher.launch does. And up here, this launcher is instantiated with this launcher encode. So let's look at encode. And encode is creating the collection indexer class and instantiating that class. And then it's calling run, and it's passing shared lists. And it also passes collection to collection indexer. And so inside collection indexer is where we're going to go next. And inside collection indexer, we have this very helpful docstring, which I actually didn't read and didn't see until this time, which is like the 50th time I've looked at this file probably, where we encode embeddings for all passages in the collection. Each embedding is converted to a code, which is the centroid ID, and a residual, which is the difference between the centroid and the embeddings. Embeddings stored according to passage order in contiguous chunks of memory. So if I have passage 0, passage 1, passage 2, I'm going to have the embeddings of passage 0, embeddings of passage 1, embeddings of passage 2, and so on. That's how I understand that. So it saves this chunk number.codes.pt, centroid ID for each embedding in the chunk. Same thing for the residuals. These are 16-bit residuals for each embedding in chunk. And then it saves doclens.chunknumber.pt, which is the number of embeddings within each passage in chunk. So very, very helpful docstring that I honestly wish I would have read earlier. The main thing I want to focus on is that it receives these passages here. And these passages, it passes through encoder.encode passages. So that's what I'm going to focus on next, is we're going to look at, let's see, encoder.encode passages. Actually, I'm not going to look at that because that basically just passes the passages through the BERT model and returns the embeddings. So we get the embeddings and we get the doclens. So the main thing I want to get from here is that EMBS are the token embeddings that our BERT model, or I guess our ColBERT model is returning. Then if we go down, there's this save chunk where it takes chunk index, offset the embeddings, the token embeddings, and the doclens. So that takes us to the index saver. And inside index saver, here's save chunk. And here's the main star of the show is codec.compress. It takes in the embeddings and it returns back the compressed embeddings. And the compressed embeddings, which we'll see in a second, are compressed inside residual codec. So if we look at residual codec, here's the compress method, line 167, and inside there, it does two things. It compresses into codes, so it takes the batch of embeddings and it compresses them into codes, and then it takes the batch of embeddings and subtracts the centroids, which gives us the residuals. So our compression is compressing the full resolution token embeddings into low bit residuals and integer values of codes, which are the centroid IDs. So if we take a look at compress into codes, the way that it gets codes is that it takes the matrix multiplication, or I guess the cosine similarity, between centroids and the batch. So centroids in my example are 1024 by 96. Batch transposed is going to be 96 by 15,198, which is the number of token embeddings in my document collection. So my result is going to be a 1024 by 15,198 matrix. I take the maximum across the row dimension. So for each of the 1024 centroid indices, I find what's the maximum, and then I take those indices, and that's what gets stored as codes. So for each of my 15,198 token embeddings, I'm saving the maximum value, the indices corresponding to the maximum value, and those are the indices of the centroids. So 0, 1, 2, 3, all the way up to 1023 are the indices of the centroids, and I'm grabbing those indices here, and that's what I'm storing as codes. So that's what codes is, and then I get my centroids given those codes, so given those centroid IDs, I look up centroids, and then I find the residual, and that's what gets passed into residual codec.embeddings, and that's what gets returned back from the compress method. So that was a quick overview. Obviously there's lots of details that I've left out, but highlighting the main concept before we get into how the IVF is built. We start with the document collection. We pass those passages through our ColBERT model, and we use the I think it's the .BERT or .d method to encode our documents into token embeddings, and that's the encoder.encode passages at the highest level. And then we use residual codec.compress to take those embeddings and compress them into residuals, which are the difference between the token embeddings and the closest centroid, and then the codes, which are just single integer values, which are the centroid IDs that those token embeddings are closest to. And we saw that closest to is the maximum value of this matrix multiplication. So it's kind of like a cosine similarity. I think these are normalized. I forget. So I don't know if it's strictly cosine similarity, but the same idea. You take the matrix you take the dot product between these two and find the maximum value, and you take the indices of the centroids that those maximum values correspond to, and that's what gets stored as the codes. So residuals and codes. And what we're going to work on when we work with the IVF are these codes, and we'll see that in a second. So the two files, or the two methods that I'm really focused on in this video, is _build_IVF. That is part of the collection indexer class. And then optimize_IVF, which is in the colbert.indexing.utils. So it's a utility function. All right, so with that background, setting our stage, I'm now going to go to this notebook. And I forgot to run all my code here, so I'll run it while I talk through some things. So what I've done is I have forked the ColBERT repo, and I've forked the Ragatui repo. And so in the ColBERT repo, one of the branches I've created is called save intermediate artifacts. And I've created a similar branch in Ragatui that points to this ColBERT repo branch. And what I've done in this save intermediate artifacts branch is throughout the two methods that I'm interested in, so build IVF and optimize IVF, I've gone through, and let me scroll down to the function of interest. So I've gone through here, and at certain points where I wanted to make sure I understood what exactly was going on, I have saved different artifacts and different intermediate artifacts in this process. So for example, here's what we just looked at. So residual codec.embeddings.load codes. So you give it index path, you give it the chunk index, and it just literally runs torch load for that PT file. So it brings the codes, and then we store them here. So these are those initial codes, those centroid IDs that correspond to those token embedding IDs that these centroids are closest to. So I saved those codes here. Bit of a cumbersome naming convention, but I just want to make sure everything's named properly. So I'm saving that as ColBERT codes before sort. And then we sort the codes, and then I save it as ColBERT codes after sort. That's many different places, so I'm going to walk through this code exactly and show how I've done that. And then in the indexing.utils file, or I guess utils.py file, here we have optimize IVF, and similarly, at different points I've saved different artifacts that I want to inspect. All right, so it looks like we have our installations ready. I have to restart my runtime because otherwise when I import load dataset, it throws some error. I always like to run import face and then face and then check that this GPU standard GPU resources attribute is part of FICE. The reason being that Ragatui runs that same check just to make sure that FICE GPU is being used and not FICE CPU. And something I also do every time I'm running this is I uninstall FICE CPU and then I pip install FICE GPU CUDA 12. This is something that works on Colab for sure. If that doesn't work for you, then I recommend, and the FICE repo recommends, installing FICE from Conda. All right, so I'm using conditional QA, and I'm going to use the first 1000 dataset items. And I'm going to go ahead and run this, and it'll take a few moments, so I will just fast forward and cut this part out so you don't have to watch this run. Okay, so indexing is now complete. And now if I look at my content folder, I can see I have all of these different artifacts now saved to my Colab content folder. So that's a great sign. That means everything has worked as expected. So now we're going to go into step-by-step inspecting these saved artifacts. So earlier on I mentioned residual codec.embeddings.load codes. That loads this 0.codes.pt file, and that has a mapping from token embedding IDs, which are the indices, to centroid IDs, which are the values. So I'm going to go ahead and I'm going to import residual codec from ColBERT indexing codecs.residual. I'm also going to import this plan.json because it has this num chunks that I want to verify, which is 1. So there's 1 chunk because I only have 1,000 documents. And then I'm going to pass it my index path and the chunk index, which is 0 because it's the first chunk. And so what it's going to do, it's now going to return the codes, which is just a single tensor with the number of items corresponding to the number of token embeddings that I have in my document collection. The minimum value is 0 and the maximum value is 1023. And so this corresponds to the 1024 centroids that we have. So again, the indices of codes are the embedding IDs, the token embedding IDs, and the values of codes are the centroid IDs. So if we look at the first line that I save in build IVF, I'm saving the codes before sort. So That's what I'm going to do here. I'm going to load in ColBERT codes before sort and inspect the same values and be like, yeah, okay, at least at a high level, this is the same. Minimum value is 0, maximum value is 1023. And if I look at some of the values, we can see that these are going to be my centroid indices. And if I double check with torch all close, I can see that directly loading codes from residual codec embeddings, which is basically what happens here in line 459, is the same thing as what I've saved intermediate. So that's another good check, and this is something that I'm going to do throughout this video. Is I'm going to check at each stage if I can manually create whatever I saved and then compare the values, compare the tensors. All right, so these are great. So we move along. So that looks good. I understand what's happening. This is a innocuous line, but it's very powerful, and we'll see why by the end of the video. So we sort the codes and return back the tuple of indices and values, and then we save those codes, ColBERT codes, after sort. So that's what I'm going to load here. And we see that this is a torch return types of sort, so it's kind of like a tuple, where I have values, and the sorted values are now from 0 up to 1023 consecutively. And this is really powerful because now we've organized our indices, which are token embedding IDs, so that they correspond to centroid IDs 0 to 1023. So now everything's kind of organized in this way where we're going from the smallest centroid ID to the largest centroid ID. So what am I doing here? I want to take a look at torch where these values, or this ColBERT codes before sort equals 0 and ColBERT codes before sort equals 1023. So we're just taking a look at, here are all the values where the indices where the centroid ID is 0, and here are all the indices where the centroid IDs are 1023. And if we look at some of these indices here, 13768, 13768 is right here. 13728 is right here. 13276 is right here. So we can kind of see like, okay, this makes sense. Confirmed that these are the indices where codes equal 0. And then if we look at these last three, 4845, 4201, 4841, we can say, okay, yeah, these are the indices where my centroid IDs are 1023. So I always like to just do some sanity checks like this visually, because now I have tangible access to this data. So now I'm going to take my manually generated codes, which I generated residual codec embeddings load codes, and I'm going to sort them. And then I'm going to see, are my sorted codes manually the same as the ColBERT codes after sort that I saved here, this line. So we're checking the indices, that checks out. We're checking the values, that checks out. Okay, great. All right, and then if we go down here, this is just destructuring the indices and the values. So codes.indices, it's storing it as ivf. Codes.values, it's storing as values. And so again, I'm just going to save ivf as ColBERT ivf after sort, values as ColBERT values after sort, and run that. And the key thing here is, and we've already kind of seen this up above here, but just to look at it again, ColBERT ivf after sort is a sequence of token embedding IDs. Now, the key thing is that alone, without any assistance, it has little meaning, right? I mean, the meaning is that it's token embedding IDs, but the sequence itself doesn't have meaning unless we have the values that correspond to it. So this 13768 alone doesn't make much sense. But with this value, we can see, oh, okay, this token embedding ID corresponds to a centroid ID of 0. So does this one. So does this one. This token embedding ID corresponds to centroid ID of 1023. So on and so forth. And then again, just checking with the values that we've already seen. So here are my sorted codes. That's the same as this IVF, which makes sense because codes.indices is IVF and codes.values is values. So that, making sure everything looks good, and then just kind of manually inspecting this index 13768. Yes, indeed, it is corresponding to a value of 0. This index 4841. Yes, indeed, it is corresponding to a value of 1023. So our mapping from token embedding IDs to centroid IDs consists of two things. It consists of these indices, which are the token embedding IDs, and it consists of these values, which are the centroid IDs. All right, so that makes sense. We move right along. The next thing that we get is another critical piece for understanding how ColBERT stores this information, is the IVF lengths object, which is a bin count of values given our 1024 partitions or centroids. So I'm going to run that here. And what we'll see is that we have a tensor with a bunch of integers. Now, if I pass my sorted codes into bin count, and sorted code 0, if we go back up here, are the values. So if I run that, then I'm going to get the same thing. And I'm just double checking that those two are equal. And they are. So my manual generation of this stuff is matching the intermediate artifacts. So what does that mean? So what do these values here mean? So let's say centroid ID equals 0. So we're going to find the indices where my codes equals the centroid ID of 0. And we're going to then look at the shape. So if we run that, we can see that there are 12 codes, or 12 centroid IDs, or 12 indices where the centroid ID is 0. And so that's what this 12 is here. If you look at a centroid ID of 1, we can see that there's 46. So 46 here. Centroid ID of 2, we can see this, there's 16, which is 16 here. So this IVF lengths is really important because it tells us, it gives meaning to this list of indices, this list of numbers. What does it mean? Well, it means that the first 12 items correspond to centroid 0, and then the next 46 items correspond to centroid 1, and then the next 16 items correspond to centroid 2, and so on and so forth. The last 5 items correspond to centroid 1023. So again, just reiterating this point that the embedding token IDs alone don't have much meaning, but as soon as you give them this context of how many consecutive values correspond to which centroid ID, suddenly now you have this mapping. And I just want to highlight that all the way back up here, where did it go? Here we go. This, again, innocuous line of codes.sort is very important because we need it to be a consecutive increasing sequence for this type of mapping to make sense. Cool. So if I look at where are my codes equal to centroid ID 2, then I take the first value, we see it's 7644. So this is the first index where my centroid ID is 2. And then if I say, okay, if we take that index and we pass it to codes, just double checking that the return value is indeed 2. So these are all just kind of like double, triple, quadruple checking these things to make sure I'm really understanding how to work with this data. And if we look at the IVF lengths, a really important value is 1024 because that's how many centroids we have created in this indexing process. And so it's really important to double check this 1024 number because we want to have 1024 of these embedding counts to do a full mapping between all of our centroids and all of our token embeddings. Something that I didn't check, so I'm just curious. I wonder what I hesitate to say 15.1. Yep, it is 15.198. So that's another good check as well. So if we take our counts of token embeddings corresponding to centroid IDs. If we sum that, we get the total number of embeddings that we have, token embeddings, which is 15,198. So this 1,024 and this 15,198, we're going to see that over and over and over again. Thankfully, because that lets us know that we're on the right track. Okay, so after IVF lengths after bin count, here we're checking that there are truly, however many centroids there are is however many IVF lengths we have. And then we reach the end of build IVF. And our last line is we're calling optimize IVF. And the important comment here we're transforming the centroid to embedding IVF to a centroid to passage IVF. This is really critical because the entire PLAD index is based on this concept of minimizing compute by comparing centroid IDs to passages. And the way we get to that mapping is by starting with the centroid to embedding IVF that we have here. And again, the IVF alone is just a sequence of token embedding IDs. What gives its meaning in this mapping is the IVF lengths, because it tells us how many of those token embedding IDs are corresponding to which of the centroids. All right, so that's our kind of halftime. So let's now go to indexing.utils.py and we go to optimize IVF. And here we have our original IVF, so it's important that here we just passed IVF and IVF lengths, because at this point the only IVF we were dealing with was the centroid to embedding IVF. Here, this naming convention is helpful because now we can see that, okay, there's this original IVF because we're going to end up with a centroid to passage IVF, which is going to be different. So right from the get-go, we get some sense of what we're dealing with. So as I'm doing every step, I save these, and then I go back here. I load the original IVF, and yep, this looks familiar. And this is the maximum embedding ID, and this is the minimum embedding ID, so this all looks good. Just going to double check that the after sort IVF and the original IVF and optimize IVF, the two different functions, are equal, and they are. I'm going to load the original IVF lengths, and again, yep, this looks good. 12, 46, 16, etc. There's 1024, and here 0 to 201. That doesn't really, it's not terribly important, but it is interesting to see that there is one centroid that has 201 token embeddings closest to it. So that's pretty interesting to see. We check it with our previous values that we had after the bin count, which was what created the IVF lengths, and that checks out to be true. All right, so we keep moving down. We have this load doc lens, which takes the index path and it loads the doc lens, and here we're building the embedding to passage ID mapping, which is exciting because that's one of the key things that we're gonna need. We flatten all doc lens, and here is my save call. So I'm saving all doc lens, so I'm gonna load that here. So all doc lens is a mapping from the passage IDs, which are the indices of this list, to the number of token or token embeddings, which are the values. So this is kind of like IVF lengths, but instead of centroid to embedding, this is lengths in terms of passage to embedding. So passage ID 0 has 4 token embeddings, passage ID 1 has 20, passage ID 2 has 18, so on and so forth. If we take the sum of our doc lens, we get the total number of embeddings, which is 15,198. Again, key number that we want to keep checking. All right, so what happens next? We're going to basically copy this code. So torch.zeros, we're going to create an empty tensor. So I'm going to do that here. It has a length that is the number of token embeddings, and it currently just has zeros. And now, what I'm going to do here is I'm going to go through my doc lens for each length. So if we go back here, so first length is 4. So offset is 0. So 0 to 0 plus 4. So for the first 4 values of this M to PID, I'm going to store the first passage ID, which is 0, right? Because it's just the index, because we're enumerating. So this is just the index of the list. And then we add our offset, our D length to our offset. So the second offset starts at 4, and then we have 20 more values. So we go from 4 to 24, and that gets saved as the next passage ID, which is 1. And then we add our 20 to our offset, so now we're starting at 24. So then we go to the next one. So our D length is now 18. So we have 24 to 24 plus 18, which is what? 42. And that's passage ID 2, and so on and so forth. So I'm going to run that here, and then let's take a look at it. And let's do this. Let's look at the first 5, and we'll see that the first 4 are corresponding to passage ID 0. That's why we have these zeros. Okay, so if I go from 4 to 25, let's do 3 from oops. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 20 values, all are 1. And that's because we have 20 document embeddings corresponding to passage ID 1. So we can just kind of see how this works out. So if we look at passage ID 4, so where in em.to.pid is the value 4? So we get back a bunch of indices, and if you notice, the key part here is that they're consecutive, because we're looping through in this loop. We're looping through consecutive indices. And then if we look at how many there are, there's 8. So PID of 4 has 8 token embeddings. We go back up here, 0, 1, 2, 3, 4 is 8. Good, it looks good. So just double checking, just triple checking that I understand what's going on here. Okay, so we go back, and this is where I save em.to.pid as ColBERT em.to.pid initial. Kind of foreshadowing that this em.to.pid is going to be used differently later on. So I load that in. Everything looks good. I had 15,198 token embedding IDs. Now, instead of token embedding ID values, I have replaced them with the corresponding passage ID. So the indices are still the token embedding IDs, but the values are now the passage IDs. And we can see that the first passage is 0, the last passage is 999, because I have 1,000 passages. And then I'm just checking that the em.to.pid that I constructed matches what I saved from the ColBERT repo, and it does. So another good check. Okay, so what was our original IVF? So if we go back here, original IVF, so first argument here, original IVF, that was IVF. And if we look at IVF, it was codes.indices. And codes.indices were the token embedding IDs. And it was just a sequence of token embedding IDs. Now, in our em.to.pid, the indices are token embedding IDs. So we can use our original IVF to index our em.to.pid. So I'm just going to read this note I wrote back here. If you recall, the original IVF was a sequence of token embedding IDs. Using it to index into em.to.pid, which is a mapping from token embedding IDs, which are the indices, to passage IDs, the value, plucks out the passage IDs corresponding to them in that order. So what this is really doing is that it's reordering the passage IDs that are here in the same order as our original IVF. And we'll see why that's important in a second. So if you run this, our first passage ID is 918, second passage ID of interest is 916, and so on and so forth. And so we've now reordered this to match, if I go back up here, to match these indices. So 13768 is now the first value. So this is the index, the index, 13728, etc. Okay, where were we? Great. Okay, cool. So if I look at my original IVF and we look at the first value, we get 13768. All right, so that's the token embedding ID. If I use that first value and then I go into m2PID and I index m2PID with that value, I get 918. So what does that mean? That means that for token embedding ID 13768, the corresponding passage ID is 918. Now the only difference here is that we're not changing any values, we're just basically reordering them so they map to our original token embedding to centroid ID mapping. So if we look at our IVF shape, it's still as long as however many token embeddings we have. Okay, let's keep moving. So that's what happens here. I'm saving this new IVF as ColBERT m2PID IVF. So I run that, looks the same, torch all close, looks the same. So now IVF is a sequence of passage IDs corresponding to the token embedding IDs in the same order as original IVF. Alone, these passage IDs cannot be explicitly interpreted. To do so, we need to know original IVF lengths, which is the count of token embedding IDs that each centroid ID map to. So going back to this, centroid ID 0 maps to the first 12 token embedding IDs, centroid ID 1 maps to the next 46, centroid ID 2 to the next 16, so on and so forth. Because this original IVF length was corresponding to the particular order, so if we go here, again, this really innocuous sort has massive implications. Because we sorted by centroid ID to go from 0 to 1023, and because we saved those indices here, which was 13768, 13728, so on and forth. Because we sorted that, that's why we had to do this indexing operation to reorder these so that now we can utilize the original IVFs, because now it's in the correct order, where the first 12 are corresponding to centroid 0 and the second 46 correspond to centroid 1 and so on. Okay, so let's move on. Next, we enter another critical juncture where we're actually now building up the final IVF and IVF lengths. So I'm going to walk through this code a little bit step by step. So I instantiate unique PIDs per centroid, which is a list, IVF lengths, which is a list, and offset, which is 0. And let's just look at, let's see, the first 10. And if we run that, we see 12, 46, 16. So what am I doing? I'm going through my original IVF lengths, and I'm pulling out each length, and I'm printing it. So basically all I'm doing is I'm printing out the first 10 values, 12, 46, 16, 12, 46, 16. Okay, cool. So we're just iterating through that list. And if we look at the first 12 items, so here's 12. So if we look at the first 12 items, we see these 12. So these are the 12 passage IDs that correspond to the token embedding IDs that correspond to centroid 0. All right, so let's now add one of the lines that we see here with a construction of PIDs. So to get these PIDs, we have our IVF, and we pluck out from our IVF from 0 to offset plus length, which is 12. So we're basically pulling out this chunk here, so these 12. And then we're passing that through torch unique. And so I want to look at that list. So if we run that, we look at this list, we have 5 unique passage IDs. So here's 889, so we have a couple of those. 894, we have a few of those. 916, we have 1, 2 of those. 918, where's 918? The first one and the last couple. And then 919, we have a couple of those here. So for these 12 passage IDs, which correspond to the 12 token embedding IDs, which correspond to centroid 0, there are 5 unique passage IDs. So that's what this torch unique line is doing. That's what this is doing here. Okay, let's keep moving. So now we're going to run this next line where we take unique centroids per ID and we append it. And then to IVF lengths, we append the shape of these. So we're going to run this. And nothing surprising. We see the same 5 unique passage IDs that we saw up here. And the shape of this is 5. So if we look at IVF lengths, our value is 5. So what this is saying, the kind of the semantic meaning of this is that centroid ID 0 has 5 unique passage IDs associated with it, and these are the 5 unique passage IDs: 889, 894, 916, 918, 919. All right, so that kind of slow build-up helps me make sure that I understand what's going on in each line. With that done, we can now run the entire loop, making sure to instantiate the variables. And we can see that we have 1024 sets of unique PIDs per centroid because we have 1024 centroids. We have 1024 IVF lengths. That's because we have 1024 centroids. So here I've saved unique PIDs per centroid. So I'm going to load that in here. Take a look at the first set, and that is indeed the 5 PIDs we looked at. And then because this unique PIDs per centroid is a list of tensors, I'm going to loop through the list of tensors and then do a torch all close with the list that I manually created. And I assert that, get no errors, so that's good. Then we go to this next line where we're taking a list of tensors and we're passing them through torch.cat. So this will now give me a single list with this many values, or a single tensor with this many values. So key difference here, right? This is no longer 15,198 because we no longer have 15,198 passage IDs, which correspond to the 15,198 token embedding IDs, because some of those tokens came from the same passage. And we took the unique set of passage IDs for each centroid. So that reduces the total number down to 11,593. So you might be wondering, and this was something I was thinking about, why is this number larger than 1,000, right? We have 1,000 unique passage IDs. So if these are unique passage IDs, why is there more than 1,000? Wouldn't that mean there's repeats? And the answer is yes, absolutely. You would have repeats. But the reason is that it's not unique globally. It's unique just to that centroid. And different centroids can have the same passage IDs associated with it, because different tokens from the same passage can be similar to different centroids. So we're still preserving the count of passage IDs, but we're preserving the unique count corresponding to each ID. So the passage IDs are unique only to the centroid ID they correspond to, which is why we have significantly more than 1,000 passage IDs. Okay. So that we have there. Then let's see. I've concatenated those, and then I save that. So I'm just going to load that again. I already did the concatenation, so I'm going to test it with mine. And that's great. That looks good. And then the last line here is just passing the IVF lengths list to torch.tensor. So I'm saving that as well. And if we look at our IVF lengths, we now have, the same thing that we saw before, 5 passage IDs to centroid, then off we go. I saved that IVF lengths after the tensor call. I checked that with IVF lengths. And with that, we are at the end of optimize IVF. Obviously, there's a little more code. There's some padding being added. There's some saving being done, etc. But our 2 main artifacts, IVF lengths, which is how many unique centroids, how many unique passage IDs are there per centroid, and then the IVF itself, which is what are those passage IDs. So this is a sequence of passage IDs, and this is how many consecutive passage IDs in that sequence correspond to which centroid ID. Those 2 combined give us ivf.pid.pt. So I'll just read through my closing thoughts. This is code that I have walked through before, I've read through before, but not at this depth, and it was obviously needed to do this because I was reading it again and I was forgetting what it meant, and it was hard to keep things in my head. So you might have seen some repetition and redundancy in how I was explaining this code, but that's just because I've gone, weeks and months not fully understanding it. So I really wanted to do that. Really wanted to drill it in. And the second thing is, even though this seems pretty straightforward and obvious, I had never done this kind of inspection or debugging or diagnosing before, where I just torch save an artifact in the middle of a script that's already there in my own fork. Very, very helpful. Highly recommend. It's it's something that I'm really going to use as a tool in my debugging toolkit moving forward. So of course, all these different artifacts and all the code that generates them is important, but I wanted to highlight a few lines that I think are really key in keeping everything sorted, no pun intended. So the first one is this innocuous codes.sort. And this is taking the centroid IDs and that are passed back from our residual codec.embeddings, and it's sorting them, so they are sorted from 000 all the way to 1023, 1023, 1023, etc. And then we're taking from that the indices, which are the token embedding IDs, and the values, which are the centroid IDs. So that's our first true mapping. And the sorting is important because those IVF lengths, right? How many of the next consecutive IDs correspond to this centroid ID? That IVF lengths is really important, and we couldn't get that if we didn't sort it. So without sorting, we wouldn't have this order from 0 to 1000, and we would not be able to construct IVF lengths. The next line that's really important is this here, because it really sets the stage for how this mapping is going to look like. You're always going to have two entities, two artifacts that alone don't make a lot of sense, but together explain everything that's important. One are the indices in this case, and one are the values. And later on, we're going to see that we have the indices and the token lengths, or the IVF lengths. And we bin count the values to get the IVF lengths. Next, we have this M to PID creation. So here's where our token embedding IDs are replaced with passage IDs. So this is the kind of handoff from token embedding IDs to passage IDs. Another crucial line is this reordering of those passage IDs based on our original IVF, based on our token embedding IDs. And the reason we're reordering it is that we can then align to these sorted centroid values. And then finally, this is the loop where the most kind of critical part takes place, where we're actually constructing our final IVF and IVF lengths. So the final IVF starts out as unique PIDs per centroid, and then we torch.concatenate them. And then the final IVF lengths are the number of unique centroids, or unique PIDs per centroid. And that is a list that we then convert with torch.tensor. So thus ends the journey from a token to centroid mapping, which is our codes, which comes from our residual codec.embeddings, to a passage to centroid mapping, which is the combination of IVF and IVF lengths. And so these two are stored in ivf.pid.pt. And so if you want to check if one index is equal to the other, ivf.pid.pt is one place you would go to immediately, check the shapes, check the values, and you would be like, okay, are the passage IDs correctly mapped to the centroid IDs? And if not, this index is different. So I hope that walkthrough was helpful. It was certainly really helpful for me, A, to go through this walkthrough as I was making it, but B, to make this video also really, really helps because I have to actually explain what the heck I was actually doing in this notebook. So this video will be published soon. I guess you're watching it, so you already know that. I'm not sure if I'm going to convert this into a blog post. It wasn't I don't have a lot of explanatory text. So if I do post it as a blog post, so the code's up there, I will post the video in there as well. I certainly won't have this branch necessarily fixed, so don't necessarily go off of the save intermediate artifacts branch, because that may change as I run other experiments. But what I've done here is nothing unique. You can fork ColBERT, you can make your own branch, you can add a bunch of torch.save calls to your content folder in Colab, run it from Colab, and you'll replicate the same thing. So that's it for this video. Thank you so much for watching. Please like, comment, subscribe, and I will see you next time.